Yeah, I just have to do that and then the, I think probably sales.
Okay. That's,
I worked on it Sunday.
oh, wow. After coming back?
Yeah, and I got to that. But second probably take with this. No, I'm too tired.
Good to rest after one weekend like that.
Well, it was Friday night. I went to bed for that.
Oh, then,
Well, it doesn't matter. I think because they just used to it. And we we're looking over it, making sure we did it all and it's pretty close.
I'm mostly grading for completes. I'm not really looking too carefully, and so as long as all the figures are there and they were reasonable, then that's all. This many students, it's hard for you to look really detail. And so, you know, I'll definitely do that for the projects for sure. So the midterm project, final project. But for the activities, just because you know, we kind of do a lot of practice. Yeah, they're mostly just practice. Yeah, so they're for educational and for fun. So I'm not really doing any assessment on the activity. Okay. Yeah.
Well, shoot, I just that would be great. It's similar to how you did
Yes.
Just doing it.
Yes.
Or whatever.
Yes, yeah, so optimization is a little bit different just because there's a lot more like mathematical stuff that I can check. And so I will be grading that one for. But just one problem. Per home.
For some people.
Second homework is going to be more challenging.
Yeah, that's notice that some of our things.
Somewhere between what's on moves and lights is without no. One cost cost us. Simply that. Thank you for a little well, oh, that's so over. I think that's like our worst.
That's my whole life plus more on top.
Yeah.
They call me at two. Yeah. What? I think that's system. They put on. We use your solar. I couldn't have one on your.
Yeah, how many times yesterday?
Oh, it's like.
Oh, yeah, like, yeah, what's he do?
I remember what I always tell people is that when you're writing a summary, you're writing to someone who hasn't seen any of the details. Managers. So how can you best communicate your results in a one-page format? And what they best kind of describes.
So we made it right now, the front element, £6 each, and they wanna do full one piece. So they're gonna add but right now it's up to 12. So we've already said 7, but he put them on the.
I'm hungry today. I'm always suffering in the second half of my
I
classes.
was scared going out.
It's too.
You got classes today?
They're back in Slack if you want to go
Right now, bro.
You have to eat a big lunch of it then.
Store, they have like. It's just scary.
It's hot.
Like I said, it's I like out of them. Wow.
But I think
The bigger one.
there's more.
Like in the got excited.
Yeah.
Should just have. Yeah.
Oh, cool.
I'll be sick.
They got it, right?
I hardly ate.
I'll give it. I should do that after. What do you think about it?
Give me great.
You?
Didn't think he had it. I saw your, you were. Which was true.
You normally have a.
Yeah.
Five?
I thought you were gonna join. No, I was here. So I was. There's like all the store. Were you having trouble visualizing? Yeah. I asked already, but I can help you pull it up. Okay.
That would be a great time.
Yeah.
Oh, yeah.
Yeah, that was my question. I didn't enjoy it. Okay, I'm gonna get it. So.
That'll ruin your day.
So then I wasn't hungry, so I didn't. Yeah. I did. Alright, well, we just bring stuff for dinner. At dinner. So. No, he told me before, like, so this is their hair.
That's all the way it is.
We're gonna stop.
Not really.
But like, well, well, I think
Some surface.
she wanted to go.
And power train. Yeah. That's why I fixed this one, so this surface right here. I fixed that one for the front.
Yeah, careful.
for the course, yeah, it's on this one. And then I guess in the diagram, it's C. So then you go in. I know the diagram, that's the slope of all the constituencies, but the course is here, right? Yeah.
Did you put it?
Yeah.
And the question. I didn't have one.
I haven't put this
We
one,
used,
cause I didn't work on it until I.
And sorry.
You put it-
Okay, man.
Like, I don't know, I just know it's somewhere.
Nice, nice.
As far as where to put it, I'm not sure yet, I'm working on it.
Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. Good to hear. All right, so we're in week 4. So we're kind of quickly approaching the midpoint, or not the midpoint, but the mid semester, I would say. So weeks 5 through whatever is 5 through 12, I consider kind of the mid semester. So this is when things start to get kind of busy for you guys. So and this class is kind of no exception. Okay, so last time we met, last Thursday, we did our second ANSYS activity. So compared to the first activity, I kind of took the training wheels off a little bit, pun intended, with the subject of the activity. And I let you guys kind of decide a lot of that on your own. So there was a lot of questions, which is great, just because we haven't gone over all the basics yet. And so last Tuesday we talked about meshing, which is one of the more important parts of FEA. Today we're going to go over the second most important part, which is boundary conditions. Okay, and so over the last yesterday and today, I've gotten a lot of questions on the very final part of the activity where you're doing the simulation on the bike frame. A lot of those questions have to do with the boundary conditions, and so hopefully after today, it'll answer a lot of those questions, and you'll be able to kind of understand a bit better kind of why the boundary conditions were applied in the way that they are. Okay. And even more philosophically, why we have boundary conditions too. All right, and so we should be able to finish up today. Boundary conditions is not too complex, but if we don't finish something, we'll put it off till. All right, remember this week, just because we didn't answer this activity last week, this week is kind of an off week, and so we're just gonna have 2 regular lectures. So regular lecture today, regular lecture on Thursday about material properties, and then next Thursday we're gonna have our next ANSYS activity. All right, so that's the plan for today. Announcements. I graded your guys' activity 1, so that you should be able to see your grade for that on Canvas. And so if you don't see your grade for that, please let me know. And for the solution, so I do have solutions for the first few activities, and so I'll post that later this week. So I kind of need to clean it up a little. It's a little bit messy from that. All right. So are there any questions I can answer before we get started for today? Okay. All right. So let's go and get started. And so the subject today is boundary conditions. So like I mentioned, just a minute ago, last Tuesday, we talked about meshing. Where meshing, I think, is one of the what I call major steps of applying FEA, especially when you're using commercial software. Okay, so meshing is always the first step. The second step is boundary conditions. So, boundary conditions are also something that's really, really important. Okay. All right, so what are boundary conditions? And so boundary conditions, kind of in a nutshell, they kind of describe all the external effects that are acting on your geometry or acting on your simulation. And so, any kind of external load or external, support, anything that's external to your geometry that's having an effect structurally on your geometry, we almost always capture those in terms of boundary conditions. Okay. So that would be kind of I would say kind of the physical definition of boundary conditions and kind of why we need that. But there's actually a very important mathematical reason for boundary conditions as well. Okay. And so if you remember, I from the first week of class, I said that FEA, at its core is what it's doing is that it's solving differential equations, right? And so you have your geometry, you have your CAD file, and what FEA is going to do is going to solve the equations for structural mechanics, it's going to solve the equations for heat transfer, fluid mechanics, whatever, right? And so whenever you have a differential equation, you need to have some boundary conditions on that equation in order to find a full solution. Okay. So there's a mathematical need for boundary conditions as well. Okay. The good news is that when you're using a software like ANSYS, you don't really think about the mathematical side of it, right? You just apply the boundary conditions as they kind of physically make sense to you, and then ANSYS kind of does the work of applying these mathematics. Okay. But I'm going to do a very quick kind of mathematical example for you, just kind of illustrate mathematical necessity. Okay. So hopefully this is like a flashback for you guys from 308 or maybe even further back, Math 250B. So let's take a second order differential equation and let's solve for its solution. Okay, so let's solve for a solution to this ODE. So we have d squared u squared is equal to 3x. So very, very simple ODE. And so we don't even need any kind of integrating factor. We don't need the characteristic equation. We can just solve this straight up by integrating. Okay. Okay. We have d squared u squared is equal to 3x squared. I'm just writing it down again just to make it convenient for me to just solve this. All right, so let's take an integral. So let's take the integral of both sides with respect to x. Okay. We have dx. And so we integrate the left-hand side, it's going to cancel out one of the derivatives, and so we have du dx equal to integral of 3x squared. So integral of 3x squared, we do kind of the opposite power rule here. We take the antiderivative, we get x cubed. Okay. But since this is an indefinite integral, right? We don't have bounds on these integrals. We just are taking just the integral just in general. We have to add an arbitrary constant to this. We'll call that C1. Let's take another integral. So we take the integral of this guy again. Once again, on the left-hand side, our integral is going to cancel out with our derivative, expression. And so we have u of x. And then on the right-hand side, we have a 1/4 x to the 4th. Okay. So that's the integral of x cubed. We have the integral of C1, where C1 is just a constant. If we take the integral of a constant, we just end up with x. Okay, so we have plus C1x. And then once again, since we're taking an indefinite integral, we have to add another arbitrary constant, and so we call that C2. Okay. And so our solution to this ODE is u of x is equal to 1/4 x to the fourth plus C1x plus C2. Just a little bit of trivia here, because our solution here is, arbitrary up to those two constants, we call this the general solution. Okay. All right. Any questions on this? Okay. Oh, question? Okay. Okay. And so, we can't, we can't say that we have the full solution yet because, we're arbitrary up into those constants. Okay. And so in order to get the full solution to this, we need to apply boundary conditions. All right, so let's use, let me give you two boundary conditions here because we have two constants, okay? So let's say we have a boundary condition at x is equal to 0, so we have u of 0 is equal to, it's equal to 18, okay? And then let's say that we have a derivative type boundary condition. And so we'll say that du dx evaluated at x is equal to 10. Say this is equal to minus. Okay. So we can apply these two boundary conditions to solve for C1 and C2. All right, so let's start with boundary condition 1. That's the simplest to do. So we have u of 0. And so we're going to take our general solution here and plug in x is equal to 0. Okay, so we have 1/4 x to the fourth. We have 1/4 0 to the fourth plus C1 times x. So that's going to be C1 times 0 plus C2, 2, 18. Okay. And so everything with the 0 is just going to cancel out. And so we get C2 is equal to 18. So let's do du dx now. And so to apply this boundary condition, we need to take the derivative of our general solution. Okay. And so we take the derivative with respect to x, we get x cubed plus C1. Okay. So we're going to evaluate this at x is equal to 10. Okay. And so we have 10 cubed plus C1 is equal to minus 5. Okay. 10 cubed is 1,000 plus C1 is equal to minus 5. Okay. So we solve for C1. C1 is equal to minus 1,005. All right, so let's go ahead and plug those in. Right, and so if we plug those in, C1, C2, we can get our full solution for u of x. So u of x is equal to 1/4 x to the fourth minus 1,000 x plus 8. Right. Any questions on this example here? All right, I'll answer a question that I think probably everyone is asking right now is, what the fuck are we doing math for in this class, right? In the FEA class, why are we doing differential equations? It's to prove a point, right? And so, just like in math, right? Just like when you're solving a differential equation by hand, your job is not complete until you apply the boundary conditions, okay? FEA is exactly the same. So your FEA simulation is not complete, or in other words, it doesn't even do anything until you apply the boundary conditions. Okay. And in fact, actually, probably, I think some of you tried this last time as well, right? And so, after you got done with the meshing of the bike crank, what some of you noticed that when you try to hit the solve button in ANSYS will give you an error. It says that, I don't know what to do without boundary conditions, okay? And so my objective for today, my goal for today is that, not only do you understand kind of, how to apply boundary conditions and how to apply them, but I think also you kind of understand kind of why they're actually needed in an FEA simulation, okay? So mathematically, we can kind of see why in this previous example here, but I think kind of once you understand the role that boundary conditions serve and kind of what they represent, you'll see why they're really needed in FEA. Okay. And so along that line of thought, one way that I like to think of boundary conditions is they're kind of act as like the instigators, or the ones that kind of cause interesting behavior in your system. Maybe instigators isn't a great word, but maybe initiators or the inputs for the for interesting behavior. Because without boundary conditions, without external effects, your simulations would be incredibly boring. Okay. Let's take an example. Let's take any object that's in this room, right? So we have a lot of objects in this room, and most of them are very boring because they're not doing anything. So let's look at a chair, right? Let's look at a chair that no one's sitting in. So right now, that chair is doing nothing, right? It's just being acted on by gravity, and no one's sitting on it or applying load, so nothing's happening, right? It's not until actually someone sits in the chair or someone comes up to the chair and just like Sparta kicks it across the room, that's when something interesting is happening, right? And so those interesting things are external effects, okay? And so we need those external effects to cause things like deformation field, to cause things like, an equivalent stress field in order for, you to actually have an interesting simulation, okay? And so one way that you can think of this, right? One way that you can think of boundary conditions that your structure or your CAD geometry is kind of just reacting to how the boundary conditions are, what the boundary conditions are doing to them. Okay. Because without any boundary conditions, without any external effects, most structures are just very boring. They just not doing anything. Right? It's not until you apply these external effects that the structure can respond or react to it. Okay. And the way that it does respond, so the amount of deformation that you see, the pattern of deformation, the pattern of stresses, that's determined by the governing equations. Okay. And so I always like to think of it that way, is that you have your structure, you have your geometry, it has its own governing equations. Okay. But until you apply the boundary condition, the structure does nothing. But as soon as you apply the boundary conditions, the way the structure will react depends on its governing equations. And so that's kind of the relationship between boundary conditions and governing equations. Okay. Any questions on any of that? Okay. All right, and so in FEA, we often like to categorize our boundary conditions in two types. So the first type of boundary condition that we'll go over are what I call constraint type boundary conditions. Okay. There's a scientific name for the constraint type boundary conditions, I guess named after the guy who formalized the theory on it. And so this is called Dirichlet. So you don't need to know that. That's kind of just trivia. But sometimes just because that's kind of how I learned it, I might say Dirichlet boundary conditions on accident, but what I mean is constraint type. And the other type of boundary condition are load type boundary conditions. Okay. And so these are called Neumann boundary conditions. So obviously, the names I've chosen for these constraint type and load type kind of have a structural flavor, right? And so you do have Dirichlet and Neumann boundary conditions for thermal FEA, for fluids FEA as well. Mathematically, they're the same. It's just that, I think constraint type and load type are a little bit easier to kind of understand and remember kind of when you're first learning FEA. All right, so let's go over constraint type boundary conditions first. So constraint type boundary conditions, they get their name because they basically constrain the solution variables to have a specified value. Okay. And so you can almost think of it as, you're forcing the solution to have a value on these types of boundary conditions. All right. So what does that mean for structural FEA? Right? So for structural FEA, our primary solution variable is the deformation. Okay, so what that means is that the deformation is the first thing that the FEA will solve for, before it solves for the stresses. Remember, the deformation is the amount that the structure will deform, in response to. Okay. All right, so that means that when we apply a constraint type boundary condition to a structural FEA, we're forcing the deformation to have a certain value, at the location where we applied the boundary. Okay. All right, so the most common example of a constraint type boundary condition that we've used before, and we're going to continue to use it in almost all of our activities, is a fixed support. And so up until this point, whenever we've used a fixed support in an ANTIS activity, what I've told you is that the fixed support should be a place where your object is being attached to or bolted to another external object that's much bigger to it. Okay, so that's still true, and so that intuition is still there. But mathematically, what's happening under the hood is that for all the locations, for all the areas that we're applying the fixed support, we're saying that the deformation of those areas has to be equal to 0. So we think back to our plate with a hole, so in activity 1. Okay. If you remember from that activity, on this edge right here on the left, we applied our fixed support. Okay. Because what we said at the time is that our plate here on that left-hand side is going to be attached to a bigger structure. Okay. If you go back to activity 1 and you look at your deformation field, what you should see is that in this area, right next to that fixed support, what you should see is that the deformation is going to be 0 in that. The deformation is 0 is because we're essentially forcing it equal to 0. Okay. And so we can see this kind of mathematically in the example we did earlier today as well. Okay. And so we look back at the example we did earlier with a differential equation, we do have a constraint type boundary condition here. Okay. And so let's look at the two boundary conditions that we specified. So we have u of 0 is equal to 18, and then we have du dx at x is equal to 10 is equal to -5. Okay. In this example here, our solution variable, or what we're solving for, is u. Okay. And so based on that fact, we can kind of identify which of these boundary conditions is our constraint type, or which is our Dirichlet type boundary condition. Okay. And that is the first one. Okay. And so what we're saying with this statement is that at x is equal to 0, at x is equal to 0, we're going to force the solution u to take on a value of 18. Thus, that is our constraint type boundary condition. Any questions on that? Okay. So let's talk about the physical intuition of kind of why we apply fixed supports and kind of where we apply those typically on our structures. And so physically speaking, you should apply fixed supports at locations where your structure is attached to something kind of much bigger than or much more stable. Okay. Because the assumption is that wherever our structure is attached to something much more stable, is that the deformations on that bigger structure are going to be much smaller. Okay. Even when we apply our forces to our structure, we're going to assume that the other thing that's attached to is not really going to move. Let me give you an example, just spoken example. So one of the most common fixed supports that you're going to see, at least for objects that are on the ground, is just wherever your structure is attached to the ground. Okay, so let's look at the chair. Right, and so if we were to run an FEA simulation on a chair, you would apply a fixed support at the bottom of all the wheels or at the bottom of all the legs, because that's where the chair kind of attaches or is sitting on the earth, the ground. Okay. And so, you can try your best, you can try to, jump up and down and kind of foot stomp the chair as much as you want, but most likely, the floor is not going to move. Right? The chair is probably going to break before you put a dent in the floor, most likely. Okay. And so, in this case, our bigger object that we're attached to is the ground, and that's where we apply our fixed support. Okay. Another type of Dirichlet boundary condition or another type of constraint type boundary condition that we can use. It's not that common, but I don't think we're going to use it that much in this class. Is a displacement type boundary. So some of you have noticed this already, and a couple of people have asked me this in the activities. Is what is that displacement boundary condition? Okay. So the displacement boundary condition, mathematically is the same as your fixed support, except that instead of setting the deformation equal to 0, you can actually specify how much deformation that it's going to have. And so you can almost think of the displacement boundary condition as kind of a more generalized fixed support. Okay, where you have freedom to kind of choose, you know, if there is kind of a preset deformation. Okay. All right, so this can be useful. You know, in cases where you have a structure and you know that it's displaced by a certain amount from its resting configuration. Okay. And so one example that I always like to bring up is a fishing rod. Okay. And so a fishing rod kind of has its own resting length, it has its own resting configuration. But let's say that you know that under a certain load, so let's say that you have a fish on a line, the tip of the fishing rod is going to displace by, you know, let's say 3 centimeters or something like that. Okay. And so instead of trying to predict, you know, how much force you need to apply to get a deformation of 3 centimeters, you can just apply 3 centimeters of deformation right at the end using a displacement boundary. Okay. All right, so for those cases where you kind of know how much deflection or how much deformation that you have already kind of beforehand, the displacement boundary condition can be useful for those cases. Okay. It's not that common, you know, more common I think is that you kind of know, instead of the displacement, you know the force or you know the load. And then you're basically trying to predict what the deformation is. But there are some kind of niche situations where you know what the deformation should be. All right. Any questions on this? Okay. All right, one final note before we move on to load type boundary conditions is that whenever you run an FEA, you know, it doesn't matter if it's structural FEA or thermal FEA or fluids, you need to have at least one constraint type boundary condition in your simulation. You can have all the loads in the world, but if you don't have a fixed support, if you don't have a displacement boundary condition in your simulation, you know, ANSYS actually won't even let you run it. Okay. And there's a couple very easy ways to kind of explain this. And so I'll give you kind of the physical definition first. Okay. So without any kind of constraint, and so without any kind of fixed support or even kind of displacement boundary condition, what's going to happen to your structure is that it's going to experience rigid body motion. So let's take our plate with a hole. Right. So we have our plate with a hole. Okay. Normally in our simulation, we would fix this plate on the left-hand side, right? And then when we pulled on it, that's what caused the deformation. That's what caused the stress. Okay. But let's say that we didn't. Let's say that we didn't fix it. Okay. But we applied our same load. So let's say that we applied our same tensile load to the structure. Okay. Without the fixed support there, this thing is just going to keep moving, right? Because there's nothing that's preventing it from moving because we don't have any constraints. Okay. And so without the constraint there, you know, your structure is just going to go flying in whatever direction you're applying the load. Okay. And so you need to have those constraints in order to prevent that from happening. Okay. It is possible to simulate motion in FEA And we are going to do an activity for that in the second half of the semester. But we're not concerned with that at the moment. So right now we're mostly just doing static simulations. Okay, so that's the physical reason why you need to have a constraint. There's a mathematical reason for it as well. Okay. And so mathematically, if you don't have a constraint type boundary condition, your solution will always be arbitrary up to some constant. So you will never be able to find the full solution because you're always going to have a constant that's kind of unaccounted for. Okay. I'm not going to go through the mathematical details for this, but if you take the very first example we did today with the differential equation and you replace the first boundary condition, so let's say that we replaced so that was our first boundary condition. Our first boundary condition said that u of 0 is equal to 18. And so if we replace this boundary condition with, let's say, another derivative condition, let's say instead we have du x at x is equal to 0 is equal to, I don't know, we'll say it's equal to 7. And so now our two boundary conditions are going to be the following. And so if we have two derivative type boundary conditions on that equation, okay, we have du dx at x is equal to 0 is equal to 7, and du dx at x is equal to 10 is equal to -5. Okay. If you have this situation, and I'll let you verify this kind of yourself, what you'll see is that it's going to be impossible to specify a value for C2. And so C2 will forever be arbitrary, will forever, not have a value assigned to it. And so, your solution is always going to be arbitrary up to C2. And actually, both the mathematical reason and the physical reasons are actually the same, right? And so if you think of this solution U as representing the deformation of your structure, okay? If C2 is arbitrary, then you can set C2 to 11 billion 54 or something like that, right? And your solution would still be valid. And what that 11 billion represents is rigid body motions. Okay. So the mathematical and physical definitions are or the reasons are the same. It's just that they're just kind of presented in different ways. Okay. Remember, you can never run an FEA simulation without at least one constraint type boundary condition. And in fact, ANSYS will actually stop you. So if you try to run a simulation with only loads, and so with only forces, only pressures, then ANSYS will say that, hey, you can't do this. You need to have at least one constraint. Okay. All right. Any questions on that? Okay. All right, so that's constraint type boundary conditions. Let's go over load type boundary conditions next. All right, so what are load type boundary conditions? Well, whereas where constraint type boundary conditions I think has a fairly narrow, well-defined kind of definition, load type boundary conditions are kind of just everything else. Okay, so everything else external to your everything else external to your system that is not a constraint basically is classified as a load. Okay. All right, so the kind of the best way that I can kind of describe it, you know, in a definition is that load type boundary conditions are any external effect that have an indirect effect on your solution variables. Okay. And so one thing to remember is that, remember, our primary solution variable in structural FEA is the deformation, okay? And so, you know, it goes without question that if you apply a force, if you apply a pressure, if you apply, you know, a torque, okay? All of these things are gonna affect the deformation, right? That's no question. But, you know, the important thing is how it achieves that deformation. Okay? And so when you applied a 100-pound force onto the bike crank, right? There wasn't a one-to-one comparison, or there wasn't you weren't able to kind of predict so that once we apply 100 pounds of force, then our deformation was going to be X, right? Because that relationship is kind of unclear. Because a lot of that depends on the material of the bike crank, it depends on its geometry, it depends on the exact nature of the equations, right? And so that's what I mean by indirect. Okay? Is that it doesn't directly specify the value like a constraint type boundary condition does. And so just because it doesn't do it directly, it doesn't mean it doesn't have any effect, right? It's just the relationship between the two is not 100%. Okay. And so let's look at the example that we did earlier today to kind of have an example for this, right? And so in our first example, we had one load type boundary condition. So our load type boundary condition from before was our derivative boundary condition. So it will du dx at x is equal to 10 equals minus 5. Okay. And so remember, you know, our primary solution variable in this case is u, okay? And so through this boundary condition, we're not directly specifying the value for u, right? What we're doing instead is we're saying that the slope of the line or the derivative of u has to equal a certain value, right? In the end, you know, this is going to cause u to have a certain value at that boundary, but we're not directly specifying. And so, you know, most of the other boundary conditions that you see in ANSYS are gonna belong to this category. Okay, and so they're all gonna have an effect on the deformation in some way. It's just not gonna be direct. But the most common ones that we're gonna see in this class we've already seen a couple through our first two activities, and so there's gonna be things like force, okay, things like pressure. You can also apply a stress type boundary conditions. Okay, so maybe you want to apply shearing or something like that. Okay. You can also apply a torque, or alternatively, you can apply a moment. Okay. There's a special load type that's present, and we're going to use this in activity 3, which is gravity. Okay. Gravity is a little bit unique because technically it's an external force, but it's not applied externally. So gravity is something what we call it a body force because it's something that's present throughout an entire body. Right? You know, there's no gravity hand that's pushing you from above. Like you feel gravity all throughout your body, and so we can apply that kind of a little bit differently. And so gravity kind of has its own kind of load. Okay. And there's lots of other ones too, but the most common ones that you'll see kind of all belong to this category. All right. And so the important thing is that when you're applying load type boundary condition, is that you want to be very kind of aware and kind of very sensitive to the real life situation that it's represented. Because oftentimes the loads are kind of where a lot of the interesting things are going to occur. And so we'll do this exercise, you know, when we do ANSYS activity 3 next week, where you know what you'll see is that in ANSYS activity 3, we're going to consider lots of different types of loads. And so we're going to consider gravity, we're going to consider wind pressure in multiple directions. We're going to assume, you know, external weights and things like that. Okay. And so for all of these external effects, you know, it's really important that you really think about, you know, what's the best type of load that I can use to actually represent this effect. Okay. Which, you know, seems obvious, right? And so you want to use, you know, the thing that makes the most sense. But, you know, when you start to do FEA kind of in practice, you know, what you're going to see is that there's usually not a clear-cut choice for how you should model these external effects. Right, and so you'll come across situations where you know you'll have your structure, and you know you have the mesh. Your mesh looks beautiful, and then you're going to apply the boundary conditions. Right, you have your constraints. So those are usually fairly straightforward. You know where to apply your constraints, but then you're going to apply the loads. Okay, you know that from you know just from intuition and from physical experience. You know that the loads are going to come from a few different sources. Right? But whether you apply those loads as a force, whether you apply it as a pressure, you know, what direction are they going to go? What magnitude are they going to have? You know, all of these are kind of really important questions that are not always easy to determine. Okay. Case in point, let's say that, you're running an FEA simulation on a very tall building, like the one that we're kind of standing in right now. Okay. A major force that's on these tall type buildings is the force that comes from atmospheric winds. Okay. And so we have the winds that kind of blow, and it's going to apply force on the building. Okay. But I think everyone should know that winds, they change direction all the time, they change magnitude all the time. And so there's a lot of uncertainty in terms of how exactly you should apply the wind force on your building. Okay. And so do you apply wind force in kind of the worst case scenario, maybe in like a type 4 hurricane, okay. Or maybe you want to simulate something for kind of an average day, right? And so those types of questions are really important to answer, because those are going to give you very different simulation results as well. Okay. All right. And so with that said, I think the most common mistake that people make when they're running FEA is that they don't really put enough thought into their load type boundary. And so you really want to think about what's kind of the best loads, or what's kind of the best boundary conditions that's most physically consistent with the real life situation. Okay. So this part is really important. And so, it's probably the most important part of today, is that, when you choose your boundary conditions, really think about the physical situation. And I wish I had kind of a better way to kind of express this. But every physical situation is going to be different. Every simulation you're going to do is going to be different. So, it's hard to really kind of say more than this, but oftentimes when I see people make mistakes in FEA, or they get results that look funny, or they don't look weird, 9 times out of 10 is because their boundary conditions are not kind of set up properly. Okay. And so really think about that, especially as we go through the next few activities, think about the boundary conditions that we're applying, and kind of think about kind of why we're applying them the way that we are. All right. Any questions on this? Okay. All right, another note that I'll make on load type boundary conditions is that they're actually not required. And so you can run a simulation with 0 loads if you want. And so you can run a perfectly valid FEA with only constraints, which kind of seems kind of unbelievable with something. Let me give you an example. Let's say we have a fishing rod. Let's say that we have a fishing rod, kind of something like this, maybe. For some reason the fishing rod is thick in the middle because I suck at drawing, but just use your imagination. Okay. All right, so let's say that this fishing rod is being held by a person. And so in this particular case, we have our fishing rod is attached to the person. This person is attached to the ground. Okay, and so we can reasonably kind of expect that this part right here, where it's being held, we can apply a fixed support here. Right, because compared to the other parts of the fishing rod, which are, not really attached to anything, this is probably as close as we're going to get to a fixed support. Okay. All right, and then let's say that we're in a situation where the fishing rod is this person has caught a fish, right? And so you've probably seen this visually, that when there's a fish on the line, the fish is going to tug the fishing rod that way, and the fishing rod is going to kind of bend quite spectacularly, actually. So have a fishing rod that kind of bends this way. Okay. Okay. And so there's a couple ways that you can apply the condition at the top, right? So because it's kind of clear from this image here, we should apply another boundary condition at the tip of the block. Okay. So one way that we can apply this boundary condition is we can apply it as a force, right? And so we know that as the fish pulls on the fishing rod, it's going to apply a force on the tip, and that force is going to cause the tip to displace. Okay. So that would be a very traditional type of simulation. So we have one fixed support, one constraint, and we have one load at the end. Okay, and the combination of those two is going to cause the rod to deform. Okay, that's one way that we can do this. Another way that we can apply the simulation and get the exact same results, same deformations, same stresses, is if we specify a displacement type boundary condition here. And so let's say that you are doing this FEA analysis because you just got back from a fishing trip, and in this particular video of someone filmed you catching this fish, this rod just snaps, and so the rod just kind of breaks apart. Okay, you don't know how much force is being applied because you don't know how strong the fish was that you were trying to reel in, but from the video you can kind of visually see how much that tip of the rod is displacing. So you can get a fairly accurate, or at least a pretty close approximation for what this displacement is. And so, based on observation or based on maybe other data that you have, you can apply that displacement directly. Okay. And so what you should see is that, up until the point where the rod snaps, you should be able to get a good estimate of the stresses inside the rod. Okay. And so if you apply that displacement directly, it's going to cause the rest of the rod to stress and displace. And then you should be able to predict and see that yes, the equivalent stress in the rod exceeded its yield strength. And so that's what caused it to snap. Okay. And so in this situation here, where we have fixed support and a displacement boundary condition, we have no loads here because everything is being applied through the constraints. Okay. And so you can have a situation like this where you have an FEA simulation without any loads at all. Okay? You just have constraints. Okay. And then last note I'll make about load type boundary conditions is that you don't, well, this is for boundary conditions in general. Okay. And so when you first learn about boundary conditions, the temptation is to try to apply a boundary condition on every single surface of your model. Okay. The good news is that that's not necessary. And in fact, probably the majority of the surfaces in any given FEA simulation are gonna have no boundary condition applied. Okay, and that's okay, because what happens when you don't apply a boundary condition on a particular surface, ANSYS actually applies a default boundary condition. And the default boundary condition, at least for structural FEA, is what's called a stress-free boundary condition. So there's no external load, no external anything applied there, and so the stress should be equal to the air that's around it, which is usually stress-free. One last practical note, and then we'll wrap it up. Okay, so I've already kind of discussed this with a few of you actually. But this is kind of a note with regards to how to apply your boundary conditions. Okay, because when you apply boundary conditions in ANSYS, you have the option of either applying it at a point, you can apply it on an edge or a line, or you can apply it on a surface. Okay, and so generally speaking, when you go to apply your boundary conditions, whether it be like a fixed support or a load, it doesn't matter. For any type of boundary condition, you want to apply that boundary condition on as wide a surface as possible. So generally, if you have the option of surface, applying your boundary condition on a surface versus a line, edge versus a point, it is always preferable to choose the surface over the edge. And if that's not possible, it's always preferable to choose the edge over a point. Okay. But you always want to make sure that you're still staying physically feasible, right? And so you're applying the boundary conditions in the right places, but you're not doing it at just a point. You're doing it over an entire surface. So this doesn't mean, for the next activity that when you go to apply the fixed support, you apply that on as wide a surface as possible. No. And so, you want to apply the boundary conditions in the correct place, but, in that area where that needs to be placed, you do it on a surface over the edge. Okay. So for example, in activity 3, the subject for activity 3 is going to be a signpost. Okay. So we have a long cylindrical object, a very long sign. It's basically a freeway sign. Okay. And so what you're going to see is that the sign is attached to the ground, and so we're going to apply our fixed support on the bottom. And so I kind of blow this up right here. The bottom of our cylinder here is going to be a circle. Okay. Right. So when you go to apply the fixed support, you can do it in a couple ways. You can either apply it directly, you can either apply it on just the edge of the circle. Or you can apply it on the entire bottom surface. And so of course, based on kind of what we just discussed here, it's going to be much more preferable to choose the entire bottom surface over just the edge. And the reason for this is that when you apply boundary conditions on kind of narrow areas like an edge or a point, you may cause some kind of weird kind of a mathematical stuff just because you have let's say a load. So let's say you have a load that's applied at one small point, right? That may cause that point to to collapse just because you have just so much pressure on one point versus distributing that over a larger area. Okay. All right, any questions on any of this before we wrap it up for today? Okay, all right, so that's all we got time for today. So when we come back on Thursday, we'll talk about kind of the last major component of FEA, which is material properties. Okay. We've already kind of talked about it a little bit, but we'll kind of just recap with a lot of that then. So thank you guys for coming today. I hope you guys enjoy the rest of the week, and I will see you guys on Thursday. Stress-free boundary condition means that there's no external load or external stress being applied. So the stress, well, so mathematically there's a stress vector that's getting applied to the FEA. That means that that stress vector is
The problem with blend and meat. University. It's a weird.
Did I answer your question?
But you said this to me. You remember Yusuf, right? From last semester? Yeah. Because I was told.
I see that one because.
Oh, soccer?
Just running. Anyway.
But anyway, it's like by my parents' road, there was this, it's called. Dude, it's so good. And I told him, you have to go. You have to go. When we went, we sent this last night. She wanted to do, he was like, no, I'm finding.
So there actually is a thin line. So there is a certain thing you can apply for. Very thin. You don't want it to go on the line around. You don't want to go on that perimeter. You want to do it on that layer. Yeah. Yeah. So just like you I would rather have the big until you find the equivalent stress greater than the yield stress.
Which is funny, because
Yeah, so I'm saying the exact same thing you did for the cycle.
I don't remember.
Oh, Scott,
Yeah, I took that. My whole mistakes. And I took those tests. Oh, Jesus.
And then when I played, like, 500, like, for the
Oh,
it's still the same. That means it's skipping this one.
Yeah.
So same thing here. So this is so you're going to basically keep increasing the force. I mean, you found it right. So this is the you got the stress to be about 17,500, and so the force is how much force you get. So it should be around maybe like 130 pounds, something like that. And so that's the answer to that.
Oh, that's the answer.
Yeah, so that's the yeah.
So what about just?
Yeah. So the 131, that's not PSI. That's actually just pounds. Remember the
Oh,
yeah. Yeah, because PSI is a unit of pressure. And so PSI is pounds per square inch. But the load that we're applying is pounds.
It's just the, you look at it,
Yep.
it's like the -1. Great. You go and you look down, it's actually negative on the bottom, which is. That's
yeah.
how big that is.